This is day 28, which is Monday. We are going to start into a new concept called gas laws. That is, I believe, pretty much the last thing that we're going to do. We might do a little bit of pH, but this is going to be a major concept that you need to know. So what we decided to do is go back to page 402 to 410. So let's look and see what we have. So when we're talking about gas laws, chemical properties of matter, that composition, the type of atoms that are represented, structures they're arranged. So when we're talking about we're talking about, it doesn't matter if it's a compound, a mixture, or a gas. It has to do with what is the composition, the types of atoms that are there, and the structures and how they're arranged. Now, kinetic energy is energy that is due to motion. Okay? So when we have kinetic energy, there is motion going on. As you remember, a solid, liquid, and a gas. Okay? A solid is where you have particles in here that aren't really moving, and they're very tightly bonded together. Then you have a liquid. A liquid actually has matter that is formed in the container that it's in. And then we have our gas. And remember, our gas are particles that are throughout this that are bouncing off of each other. So, kinetic molecular theory is a behavior of matter in terms of the particle's motion. So what we're going to be doing with gas laws is we're going to be looking at the kinetic molecular movement of these particles and what happens. Now, when we're talking about gas, kinetic molecular theory, we're talking about size, we're talking about energy, and we're talking about temperature. Since gas particles are far apart, they're not significant attractions or repulsions, and then you have a motion, which is an electric collision, or no kinetic energy is lost. So when we have something that is in a container, there's no energy that's being lost because it's all inside. Okay, so energy is Ke equals half the mass times the volume. So that is kinetic energy. Temperature is measured by an average of kinetic energy in a sample matter. So let's talk about what's happening in a gas particles and what's happening in a container. So here it was basically showing us where you have a compression going on here, and this is a particle gas, and you have a stopper that's pushing it down, and then that stopper would eventually expand and expand some more. So when you're talking about an average container of gas that is just sitting there, you can compress it, which means that you can make it into a smaller area, or you can pull the plunger out and do the expansion of it. It's kind of like a syringe, and when you have a syringe, you can push it in, you can pull it out, and as you do that, those air particles are going to be compressed or have more room. Okay? So, diffusion. You know about diffusion if you've ever been and sprayed perfume. Okay? Diffusion is described by the motion or the movement of material through another. So when I think of diffusion, I think of somebody spraying perfume, and that perfume is sprayed on them, but then it sprays throughout the whole room. We have the Graham law of effusion, which is the rate of effusion for the gas is inversely proportional to the square root of its molar mass. What does inversely proportional mean? What that means is this. If something goes up, the other goes down. Okay? That's an inverse relationship. When one thing goes up, the other thing goes down. So then we have the rate of infusion, which we have this funny looking symbol here, equals 1 square root of the molar mass. So gas pressure is gas exerted as they actually are colliding. Pressure is force per unit area. You have what's called, in a liter, there's 10 times 22 gas particles that are in 1 liter. And then it talks about how they came up with 760 millimeters of mercury, 1 atm, and 760 torr. these numbers here are going to be what we're going to be using in gas laws. Gas laws, and the thing I want to think about, if you are talking about 1 atm, 760 torr, 760 millimeters of mercury, we're talking about units, kind of like meters, centimeters. It all is the same thing, but it's based on the instrument that you are measuring in. Kind of like a scale and a triple beam balance. They both have the same mass, but they have different units because those units are representing of that instrument. So let's look. They also talked about a barometric instrument was used to measure atmospheric pressure. So before, the gas is here, and then this level here, this liquid is in a level, it's in a closed inner, and that's vacuum up there. But then when you open up the container of the gas, you will see that there are different levels of that liquid. Now it's not even, now it's either pushing to the end or pushing to the left or the right. 1 Pascal equals 1 Newton per square meter, which is 1 PA equals 1 N divided by M squared. 101.3 kilopascal when you have 0 degrees as far as temperature goes. 1 atmospheric pressure, or 1 atm, equals 760 millimeters of mercury, 760 torr, and then 101.3 kilopascal. These numbers here are what we're going to be using the rest of this week. Dalton's law of pressure is the total pressure that is mixed of a gas. Some of the pressure with all of the gases are mixed. So what we're going to be doing is we're going to be using this equation here. P total equals P1 plus T2 plus P3, all the way, and you're adding all the pressures together to get the total. So the sample question that was in the book talked about, and let's look at it. Sorry, I need my book. It tells us that a mixture of oxygen, O2, carbon dioxide, CO2, and nitrogen, N2, at a total pressure of 97.97 atm. What is the particle pressure of O2? The particle pressure of CO2 is 0.70, and the particle pressure of nitrogen 2 is 0.12. So the only thing we're doing here is we are taking these numbers, okay? Particles of nitrogen, particles of carbon dioxide, and we're looking for the total of that. So the only thing we have to do is we just have to go say, all right, if I have the total, I am looking for the particle that we don't have, which is P in particle oxygen 2. That's what we're looking for, right? So what we're going to have to do is we have to take our 0.97, figure out a way to move this so you can actually see it. I think you can. Okay, so what you're going to do is you're going to put 0.97 and you're going to subtract 0.70 and subtract 0.12, and I get 1.5 E negative 1. That is the correct answer, but I would prefer it to be in normal mode. So I'm going to clear it and enter it. And I'm going to hit it again, and I get 0.15 atm is my answer. Okay, question number 1 on our questions. It says the particle pressure of hydrogen gas is a mixture of hydrogen and helium with a pressure of 600 millimeters of mercury. What is the particle pressure of helium? Is 439 millimeters of mercury. So we have the total, and we have helium, and now we're looking for hydrogen. So the only thing we have to do is just take 600 from 439, and we get 161. We're going to use the same units here, millimeters of mercury. As you remember, our units are atm, millimeters of mercury, or kilopascal, or torr. These here, you have to remember them, okay? Because these numbers are very important. So the next one says, find the total pressure of the mixture that contains 4 gases, particle pressure, 5.00 kilopascal. I'm going to say that, call that pressure 1. 4.56 kilopascal. I'm going to say that's pressure 2. 3.02 kilopascal. I'm going to say that's pressure 3. And 1.20 kilopascal. And I'm going to say that's pressure 4. So what we're looking for is we're looking for pressure total. If we're looking for pressure total, the only thing we got to do is just add them all together to get our pressure total. And then number 6, which is a 6 on here, and I called it 1, 2, and 3. Sorry. Find the particle pressure of carbon dioxide in a gas mixture with a total pressure of 30.4 kilopascal. Well, that's my total pressure. And it says the particle pressure of the two gases that are mixed is 16.5, which is I'm going to say it's my second gas, and 3.7, which I'm going to say my third gas. So I'm going to take my total minus my pressure 2 minus my pressure 3 to get my pressure 1, which that's what I'm looking for here. Okay? And then the last thing we want to talk about is using Dalton's law. So at the very top it says, after knowing the pressure, volume, and temperature of a gas helps us calculate the moles of gas. So that is where we are. Okay? So this is what we're going to be doing. What we're going to be doing, is we're going to be taking these answers that you're going to be doing, and we're going to use them as credit on your test that you're going to take. Now, the last test that you took, and we were talking about grams to moles, moles to grams, all of that. What we're going to do is we're going to take the test that you took and the quiz that you took, and then we're going to look at the assignments that you did just for grams to moles, moles to grams. And if you did those assignments, we're giving you, I think, 10 points per assignment, extra credit. Now listen, I understand that you're tired and you want to be done, but you just got to keep pushing through. You are juniors getting ready to be seniors, and you have to learn that, look, sometimes you have to do something that you don't want to do. But I promised you I'd be here for you. Now, I stopped videotaping videos because no one said they wanted them. But I can tell, based on your test and your quiz grade, you need me to help you. Can I say, keep your ISM book up to date. Keep the reading assignments, and if you don't want to read, I don't care. You don't have to read. If you can read and say, look, Miss Sloan, I read and it's just frustrating to me and I don't understand it. Well, you're going to have to learn how to do that. So I want you to try to use the videos and write this stuff down. Keep it in your notes so you can go back on your test and check it out. Have a good day.